Hello everyone. Our lesson will be today about number systems. Before I start our lesson, I would like to talk about the midterm exam, which will be in the 23rd of November. We haven't chosen the time yet, but I will announce it soon on the website. So please check into the website like every day. And yesterday we had online chat and no one appeared again. So I'm expecting you guys to do online chat next Wednesday, same time at 8 p.m. at 6 p.m. Excuse me. So it will be at 6 p.m. Today our lesson will be about number system. Common number system. We know that the computer doesn't understand the human being language. So it only understands binary language, which is convert like our human being language to computer language, 0 and 1. So our language will be converted to 0 and 1. So now we will talk about, or we're going to show you how to convert decimal, octal, and hexadecimal to binary. So in this table, it shows the common number system, which we have decimal, binary, octal, and hexadecimal. So decimal, it's in base 10. Binary, it's in base 2. Octal, it's in base 8. And hexadecimal, it's in base 16. The samples of the system, decimal, it's from 0 to 9. So it starts from 0 until 9. So this makes 10. Binary, only two numbers, 1 and 0, or 0 and 1. And that's all the binary that understand. Octal, it's from 0 to 7, and hexadecimal starts from 0 to 9, and then from A to F, etc. Used by humans. So decimal, it's used by human. Binary, it's not used by human. Octal, it's not used by human, and hexadecimal is not used by human. But these, let's see if it's using computer or not. All of them are not using the computer except the binary. So binary is the only one which is used in the computer. Quantities and counting. This table shows us like the numbers of the decimal, binary, octal, hexadecimal. Common number system. We have decimal, binary, octal, and hexadecimal. So each one is represented in base. So decimal is represented in base 10, as we see here. Binary is represented in base 2. Octal is represented in base 8. And the hexadecimal is represented in base 16. So this is the sample, as we see in here in this table. This is the sample of each one. So from decimal, it's start from 0 until 9. Binary only expect 0 and 1. Octal from 0 until 7. And hexadecimal from 0 to 9, and then starts with the number. A, it's represented for number 10. B, it's represented for number 11, etc. until F. So which one is used by human? Decimal is used by human. Binary is not used by human. Octal is not used by human. Hexadecimal is not used by human. Which one is used in the computer? Which system number is used in the computer? Decimal, it's not used by the computer. Binary, it's the only one which is used in the computer. Octal is not used by the computer. And the hexadecimal is not used by the computer. I'm sorry, it's used by the computer, in the computer. So all of them are not used except one of them, it's the binary. Quantities and counting. This table which shows us like the sample of them, like until where it does start. So decimal, it starts from 0 until, we can say until like infinity. Binary starts from 0 to 1, but represented in the decimal, we can see it now, like 0 is represented in binary to 0. 1 is represented in binary in 1. In octal is represented as well as 1. Hexadecimal is the same one. So this table shows us exactly how is it represented. Each one of them, how is it represented in the other one. This table shows us again the representation of the numbers in each system binary, or decimal, or octal, or hexadecimal. Now conversion among bases. So we're gonna show you how to represent or how to convert octal to binary, or decimal to hexadecimal, or from binary to octal. So it's going to be mixed. So I'm gonna show you all of them, but it might take us like 2 or 3 lessons to explain all of this. A quick example. We have 25, number 25 in base 10. Base 10, it's decimal. So 25 representing in base 10 in decimal, it's equal to 1101001 in base 2, which 2, it's represent the binary. And again, it's equal 31 in base 8, which is the octal. We said before, 8 is octal. And which is again represented 19 in base 16, which is hexadecimal number. So 25, we can see it how it is represented in the computer. It takes it like 11001 in base 2, which is the binary. And again, 25 in base 8, which is octal, 31, it's equal to 31. And 25 again is represented as an hexadecimal in base 16, which is 19. So this is like a very easy and simple example of how we convert. But now we're gonna come and show you exactly how you convert numbers to system numbers, binary, decimal, hexadecimal, or octal. So now we're gonna talk about only decimal to decimal, from decimal to decimal, how we represent it actually. So now I'm gonna convert, or I'm gonna show you how to convert 125 in base 10, which is the decimal, in decimal. But how is it 125 here? So we're gonna write it from the bottom to the top. As we see here, we take this number 1, we write it here, number 2, we write it here, and number 5, we write it here. So we read it from the bottom to the top. So it's equal to 125. And we multiply it by the base. But the base has a weight. So we write it as this, from the top to the bottom, 0, 1, 2. So 5 multiplied by 10 to the weight 0, so it's equal to 5. 2 multiplied to the base 10 in weight 1, so it's equal to 20. 2 times 10, it's 20. 1 times 10 in weight 2, it's equal to 100. And after this, we will just add the numbers here, and it gives us exactly the same number, 125. So this is how we represent the decimal into decimal. Now I'm going to show you how to represent the binary, or convert the binary to decimal. We're going to convert binary to decimal. Technique. The technique is 1, multiply each bit by 2 to the weight n, whereas n is the weight of the bit. Second thing, the weight is the position of the bit starting from 0 and the right. Add the result. Now we'll explain it exactly how we convert binary to decimal. We have one example here, 101011. So this is in base 2, which is binary. We are going to convert it to decimal. So this is the result in decimal. But first of all, let me show you how to convert the binary to decimal. 1, we write it like this. From the left to the right, we write it here, from the bottom to the top. So we take this number, we write it here, 1, then we take the 0, then the 1 again, 0, 1, 1. So this number, we write it from the bottom to the top, and we write here the base. So this is time, we multiply it by the base 2, which is binary, representing in binary. And we write the weight. The weight is 0, 1, 2, 3, 4, 5. And now we just do the multiplication, which is here equal 1. Again, here 2 is equal to 0. It's equal to 0 because it's multiplied by 0. And 1 is multiplied by 2 to the weight 3, which equal to 8. And 0 multiplied by 2 multiplied by the weight, it's 4. So it's equal 0 because we multiplied it by 0. 1 multiplied by 2 to the weight 5, which equal to 32. So we add this number, and it gives us exactly how we convert it. So 101011 in base 2, it's equal exactly to 43 in base 10, which is decimal. So this is how you convert it from binary to decimal. There is another way to do it, which is you can do it like this one in base 1, base 2, 4, 8, 16, 32. So this one is 32, 16, 8, 4, 2, 1. So each one of them, you can just underneath write it. Each one, like here is 32. We have 32. We write 32. We go here, it's 8. We write 8. And here 4. We write 4. And we have 1. We write 1. We add all of them, and it gives us exactly the same, 43 in base 10, which is the decimal. Now I'm going to show you how to convert octal to decimal. The technique for this, it will be about, like, it shows us like how to multiply each bit by 8 to the weight n. Where is the weight of the bit? And the second thing, the weight is the position of the bit, starting from 0 and the right. Add the result. In the end, we add the result. For example, we have 724 in base 8, which is the octal. 4 times multiply, we write it like this again. All of them are we have to do the same technique. 7, we write it here, 2 here, and 4, we write it here. So from the bottom to the top, you write it. And then we multiply to the base. We have to consider the weight, 0, 1, 2. So 4 times 8 to the weight 0, it gives us the result 4. 2 times 8 to the weight 1, it's 16. 7 times 8 to the base 2, it's 448. So this number in base 8, which is the octal, it shows us exactly when we converted 468 in decimal. So 424 in base 8, 468 in decimal. So this is how we convert it from octal to decimal. Again, it's the same technique. You have to write it from the bottom to the top, and we have to multiply it by the base. So it's if it's binary, we multiply it by 2. If it's decimal, we multiply it by base 10. If it's hexadecimal, we multiply it again by base 16. But we have to consider the weight of the value. And now I'm going to show you how to convert hexadecimal to decimal. Technique again, multiply each bit by the base 16 to the weight of n, whereas the n is the weight of the bit. Second thing, the weight is the position of the bit, starting from 0 and the right. And the end, we just add the result, and it gives us exactly the number of converting. ABC. So in hexadecimal, we can write ABC, or let's say 1A or B or 2BAC. We can do this. So this one, it shows us exactly number in decimal, in base 10. So hexadecimal, it's base 16, actually. And decimal, it's base 10. So we're going to convert hexadecimal to decimal. Again, we write it again from here, from the left to the right. But here we write it from the bottom to top. So A, B, and C. A, B, and C. So now to the base 16, and we have to consider again the weight. So C multiplied by 16 to the weight n, which is 0 here, it gives us exactly 10. 10 multiplied 1, it's equal to 12. B multiplied by 16 to the weight n, which is 1 here, equal to 11. 11 by multiplied by 16, it's equal to 176. A times 16 to the weight 2, it equals again to 10. 10 multiplied by 256, which equal to 2,560 in base 10. We add this number, again we add this number, and it shows us the exact result of this number in hexadecimal and decimal. I'm sorry, it shows us the result of decimal because we are converting from hexadecimal base 16 to the decimal of base 10. Now we are going to convert from decimal to binary. Decimal to binary, the technique, we divide by 2 because we are converting from decimal to binary, divided by 2, keep the track of the remainder. So we have to keep the remainder on the side. First remainder is the bit of 0. So first remainder is the bit of 0. Last significant bit. Second remainder is the bit 1, etc. So now I will show you exactly how this technique is going to work from decimal to binary when we convert it. Example here, we have 125 in decimal. We're going to convert it to binary. So what we will do, we divide it. We divide this number by the base 2. So 125 divided by 2, it's 62, and the remainder is 1, as we see here. 125, we divide it by 2. It shows us 62, and the remainder will be 1. Again, we divide 62 by base 2. It shows us here 31. So we don't have a remainder, but we still write it. So you have to write the remainder. Again, we divide 32 in base 2, which is 15, and we write the remainder, which is 1. Again, we divide 15 to base 2, which is 7, and the remainder will be 1. Again, we divide 7 to the base 2, which is 3, and the remainder is 1. Again, we divide 2 to the base 2, we divide it by 3, and shows us 1, and the remainder will be 1. 2 divided by 1 is 0, and the remainder will be 1. Now, 125, we write it from the bottom to the top again. So this one will show us like 125 in base 10 to the binary in base 2. So we write it from here, 1, 1, 1, 1, 1, 0, 1 in base 2, which is the binary. Our lesson, I know, introduction to computer, but this you have to know. Like, you have to know how the computer works, how the computer does his job, and how we the computer convert our language to the machine language. So we have to know how the computer does that. So this is the number in base 2. We write it from here, 111, 1101 in base 2. I know it's all numbers, but we have to study it still. Now I'm going to show you how to convert octal to binary. Octal to binary now. Technique, convert each octal digit to a 3-bit evaluation binary representation. So we have here 705 in base 8 equal to what in base 2? From base 8 to the base 2. So 705, this is how converted in base 2. It's 7 equals to 111, 0 equals to 000, 5 equal to 101. So this is in base 1, this is 2, for base 4. So we add 4, 1, it's 5. So this is base 1, base 2, and 3. So we add them, 4 and 1, it's 5. 0, it's 0. 1, 2, and 4. 4 and plus 2, it's 6. Plus 1, it's 7. So this is how it shows us the technique, how to do it, how to convert from octal to the base 2. 705 in base 8 equals 2. We write it from here, 111, 000, 101 in base 2. We have to write always the base. Now I'm going to show you how to convert hexadecimal to binary. And this will be the last one we're going to convert for today. Convert each hexadecimal digit to a 4-bit equivalent binary representation. So 10AF to the base 16 equal in what in base 2? Hexadecimal, base 16, to binary, base 2. We have here 10AF. Now we will write like how we convert it. We write base 1, 2, 4, and again 8. 1, 2, 4, 8, 1, 2, 4, 8, etc. So we have F, which is equal to 15. So F, it's 1, 2, 4, and 8. 8 plus 4 plus 2 and plus 1 equal to 15. Again, A, it's number 10 in hexadecimal. So, but we have to write it like this, 1010, which is E8 plus 8 plus 4, which is 10. 0, it has to be all 0 when you have number 0, and 1, 0, 0, 0, 1. So 10AF in base 16, it's equal to this number in base 2. That's it for today. I would like to send some homework for this assignment, like for this lesson. I will send it to you on next week, inshallah, and we'll continue this topic next week again.